Good morning. Um, am I audible?
Yes, sir.
Good. Very good. Yeah. Yesterday Sunday I had to arrange a discussion class. Initially, my plan was to have a give you an assignment and then have this discussion class to discuss the problems on the assignment as well as some other problems. But yesterday's I had to change my plan because there was an unexpected meeting uh, to which like, I must attend. So I had to arrange you something, and discussion class came before giving you an assignment. But hopefully, before the end of this week, I will give you an assignment. Um, we are a few days behind our plan, but today I will uh, finish our first chapter and move on to uh, the second chapter. Um, I think the notes for the inverse functions is on the LMS. I, I will check it. If I updated the learning management system last week, I think it should be there. If it is not there, I'll go and check it. Hmm? Uh, all right. You should see my notes now. We talked about functions in general, then graphs, uh, especially how we can deduce the graph of an unknown function using translations, rotations, and reflections, and some scaling on a graph of a known function. And inverse functions, one-to-one functions. So one of the applications of one-to-one functions and inverse functions is exponential and logarithmic functions. Exponential functions, you all know them very well. Powers. Yesterday, I asked Mr. Bandara to discuss one problem on exponential functions because then it is sort of like a warm up for this class. I hope he had enough time to go through that problem. Okay, okay, I will check the LMS after this class. Hmm? So exponential and logarithmic functions. We'll talk about the basic definitions, basic properties of exponential functions, and how to solve equations involving exponentials, domain, codomain, graphs, and something called the natural base. Exponential functions are very important, especially in life sciences, because population growth, not only human population, but also uh, things like uh, growth of a bacteria colony, maybe growth of an ant colony, anything like growth of any population, unless there is an external factor affecting the growth. Usually, population, at least at the beginning, it is exponential. Population tend to increase rapidly, and after some point, there are natural limitations. The competition for food, competition for space and a lot of natural restrictions come into play. And then after a certain point, population growth is not exponential anymore. But at least at the beginning, uh, population growth is exponential. Then something called continuous compounding. This is one of the early motivations for exponential function. So imagine a bank account. So in the bank, they can compute your interest for the bank account at the end of every month. So they compute the interest and add it into your account, add it to your basic principal value. So after adding the principal value, uh, for the next month, if you did not deposit or withdraw any money, now your principal amount has grown by a little amount. So in the next month, interest will be added for the initial principal value plus uh, interest for the first month. So likewise, this interest get added. So this is called compounding interest. So this is for a single month because banks usually calculate the interest at the end of every month. Now imagine the bank changed their policy and started compute their interest daily. So at the end of every day, they will do this process. And if they would, they can even go further and compute the interest at the end of every hour, every minute, every second. Likewise, they can shrink this time. So this is not like something happen in real world, but theoretically you can uh, think of the limit of this process. They can shrink the time interval, month, maybe bi-weekly, weekly, daily, hourly. So likewise, they can shrink the time interval to zero. So what would be the theoretical outcome of this compounding process? With like really small time intervals. So this was a this is kind of interesting curious problem. So people thought about this, and what they found was uh, the exponential function. Continuous compounding was a very early motivation, uh, like 200-300 years ago. People thought about that seriously. Then radioactive decay, radiocarbon dating, temperature and reaction rates. Uh, there are many more uh, motivations. So there are many more applications of exponential functions. Um, so first thing I'll teach you is the form of an exponential function. Exponential function. So it is like the power function. Remember, x squared, x to the third power, x to the fourth power. Those are called power functions. So in a power function, the power is constant, but base is changing. So think about x to the fourth power. 4 is constant, but x is in the base and it is changed. For the exponential function, we interchange this order. Now, base is a constant, but power is changed. When we change them, their roles, we get something completely new. So, exponential in an exponential function, base is constant, x is changing. Um, uh, Now, when we change, so when we fix the value for the base, when we choose a constant for the base, we need to be a little careful because if the base is a negative number, we run into problems. Like, for example, think about the square root of -1. It is like -1 to the power 1/2. It is not a real number. We know inside the square roots we cannot have negative numbers. So for the same reason, the base cannot be negative. So base must be either 0 or some positive number. On the other hand, if base is 0, 0 to any non-zero power is 0, 0 to the power. Third power is 0, 0. Second power is 0. Likewise, powers of 0 uh, doesn't add any value. So we don't need 0. The same thing happens for b equals 1. If the base is 1, any power is again 1. So 0, 1, and negative numbers are not that interesting. We can think about all the other values. We can choose any other value for base. So we have two cases. First one is base can be a number between 0 and 1, and base can be a number bigger than 1. So we have two choices. And these two choices are not that different. So let me show you an example. So imagine you choose b to the power, b equals 1/2. So then b to the power, sorry, b equals 1/2. So your base is 1/2. If base is 1/2, half to the power x, you can write it as 2 to the power minus x. So you can take this fractional base, something in between 0 and 1, some fraction, and change it to something bigger than 1 by changing x to minus x. So for example, 1/2 is not unique. You can choose like 3, 1/3, b equals 1/3. In that case, 1/3 to the power x is same as 3 to the power minus x. So likewise, you can take any number between 0 and 1 as the base and make it to something bigger than 1. So when you do so, x get changed. X change from a positive value to a negative value. Right? Let me open my writing pad. I always get mixed up these buttons and somehow lost in the middle. All right. So right. So say you have this graph of graph of 2 to the power x. When x is 0, y equals 1. 0, comma 1. And for positive x values, it goes like this. And for negative x values, it goes like this. Always this is positive. The power function, or exponential function, is positive. It never goes below the x-axis. It's very small. Now, to find the graph of 1/2 to the power x for 2 to the power minus x. Now you need to change positive x to negative x. So you take this guy and make it, you need to make it to a negative number. So when you change some positive x to negative x, it basically changes, you flip the direction of x-axis. You change the direction of x-axis. That means you keep the y-axis in the same place, you rotate the x-axis around the y-axis. So the graph gets changed. It goes like this now. It still goes through 0, 1, but now for positive, for very large x values, you're getting very small y values. So this is the graph of 1/2 to the power x, rotating the graph around y-axis. Remember, this is what happened when you know the graph of y equal f of x and you want the graph of y equal f minus x. You rotate the x-axis above the y-axis. So because of this, you can see the symmetry. For b bigger than 1, we have this usual behavior in this left-hand side picture. And for fractions, like numbers between 0 and 1, you have this other shape. That is exactly the mirror image of the previous graph around y-axis. It is like y-axis is like a mirror, and image inside the mirror is what you get in the right-hand side. So even though you have two intervals for choices for b values, now because of this symmetry, mirror symmetry, you can choose your b to be bigger than 1. So for exponential functions, if you know the behavior of function for base value bigger than 1, base value is bigger than 1, then you know about all possible exponential functions. Because negative b values and 0 and 1 are not possible, not interesting, problematic in some cases. But for other cases, it is enough to know about b bigger than 1. So basic properties. Now, if you go back to the picture, this graph has some interesting properties. Y-intercept happens right over here. At the y-intercept, x value is 0. If x value is 0, y value is always 1. 0th power of any number, any positive number is 1. Other than that, this is a graph of a function. You can see it using the vertical line test. If you think about any vertical line, it intersects the graph exactly at a single point. So it passed the vertical lines test. And if you think about the horizontal line test, we use the horizontal line test to check whether the function is one-to-one or not. So the graph in the left-hand side is clearly past the vertical line test. If you take any vertical line above the x-axis, it intersects the graph exactly at a single point. And for negative y values, we don't have a graph. So that's perfectly fine. So this is not only a graph of a function, but the exponential function is 1 to 1. So that is important. Right. So exponential function is 1 to 1. If b to the power x equals b to the power y, then x equals 1. That is how we define the 1 to 1. And we have inequality rules. So the first inequality rule says, think about b bigger than 1. So if b bigger than 1, we should look at the left-hand side graph. Take any x value you like, then take something bigger than that. Take some other y value bigger than x. Okay, so for that x, you get a small power. When you raise b to the power x, you get a smaller value. For large x values, you get large powers. B to the power very large number is very large. So that is exactly what this first point says. For very large x values, you get large powers. This is what happened for b bigger than 1. If b is smaller than 1, you get the opposite behavior. Large x values give you smaller y values. One of the key important properties of exponential functions, it turns products into summations. When you multiply two powers with the same base, powers get added. So it changes products to sums, and it takes portions and gives you differences, and it takes powers and return you multiples. So these are very important properties of exponential function. So using this one-to-oneness and all the rules that we learn, we can solve equations involving exponential function. So imagine, recall the one-to-one property. One-to-one says if b to the power x equals b to the power y, then x equals y. As long as you have the same base, powers must be equal. So for this equation, 4 to the power x square plus x equals 16. We don't have any unknown values in the base. We have unknowns in the exponent. So to solve this equation for x, we need to isolate. So we need to get rid of the base. We need to somehow have the same base, possibly with like same base but maybe different powers. So this is not that difficult. You have done this already multiple times in your school. For 16 is 4 to the power 2. So yeah, we are using the one-to-oneness property. So we wrote 16 as 4 to the power 2. Now, when we have the same base, exponents must be equal. So x squared plus x equals 2. Now, we are back on the track with these familiar quadratic equations and maybe with simple linear equations depending on the exponents. So now solve this equation for x, and here you get two solutions. And if you substitute back, for example, if you set x equals 1, in the initial equation you get, in the left hand side you get 4 to the power 2 equals 60. that is okay. And if you set x equals minus 2 square is 4, 4 minus 2 is again 2. Again, you get the same equation. So both of these solutions satisfies the actual initial equation. So we have both are actually solutions. It is very important to substitute back and check whether the solutions actually satisfy the given equation. You know, in our discussion about rational equations and radical equations, we saw this is not the case sometimes. When you square things, when you cross multiply things, you are introducing these external solutions. So some you need to make sure all the solutions are actually satisfying the given equation. All right. So look at this. Second example, asks you to solve this equation. 2 to the power x equals 2 to the power x times 3 to the power x plus 1 equals 108. So how do you solve this? Again, you need to somehow convert this equation into something like b to the power x equals b to the power y to apply the one-to-one property. Now take the left hand side and simplify it and make it to a single power and look at the base of that power. And then go to the right hand side and write that number. Write the number, constant number in the right hand side as a power of that base in the left hand side. So let's see. Here we have 3 to the power x plus 1. In the exponent, we have x plus 1. That means 3 to the power x plus 1. We know by the product rule, 3 to the power x plus 1 is same as 3 times 3 to the power x. So 3 times 3 to the power x. Now you can combine 2 to the power x and 3 to the power x using the product rule. When you have this something like a to the power x times b to the power x, it is ab to the power x. So in the left hand side now we have 6 to the power x times 3 equals 108. Divide both sides by 3. So you get 6 to the power x equals 108 divided by 3. And 108 divided by 3 is 36. 36 is 6 to the power 2. So 6 to the power x equals 6 to the power 2. The only solution is x equals 2. Equation is very simple. If you're familiar with these rules with exponential functions. Third example. It looks kind of complicated, but again, applying these simple rules about exponentials, we can solve it. The left hand side we have third root of 5 raised to the power x plus 2 equals 5 to the power x squared. Again, convert everything into the same base. So left hand side, the left hand side base is cubic root of 5. You can think of it as 5 to the power 1/3. So 5 to the power 1/3 raised to x to the power 2. Sorry, 5 to the power 1/3 raised to x plus 2. You have these repeated powers. You take a power of a power, then powers get multiplied. So it 5 to the power x plus 2 divided by 3 equals 5x squared. Now the base is same. Base is 5 for both sides. Solve the equation for x. So you get x plus 2 equals 3 times x squared. Solve the quadratic equation for x. And to solve the quadratic equation, you have few different options. Factorization is one of them. Quadratic formula is one of them. And completing square is another one. So you can use any method you like to solve the quadratic, but you should get two solutions. So likewise, by applying these basic properties to manipulate exponential functions, you can solve exponential equations. Do you have any questions about solving exponential equations? Okay, somebody wants to go back and see the rules about exponential functions. Right. Let me see. The first property is one-to-oneness. First property is one-to-oneness. Then product rule. When you multiply two exponential expressions with the same base, exponents get added. In quotient rule, the same thing, but now instead of multiplication, we have a quotient. Right? And then power rules. Power of the power, b to the power x raised to another power y is b to the power x times y. Then ab to the power x is a to the power x times b to the power x. Whenever you have something for multiplication, there is corresponding rule for division or quotient. Right? Now, let's go back and summarize what we talked about. For the exponentials as a function, base is fixed. Base is fixed. We cannot have negative numbers for the base. Once again, because think about the x minus 1 to the power 1 half, square root of negative 1. Square root of negative number 1 is not a real number. We cannot take square roots of negative numbers in the real domain. So to avoid those kind of complications, we choose positive numbers for base. But the domain of exponential function is not the value for b. B is the base. X is in the exponent. The domain is what set of all numbers that we can substitute for x. For that, you can choose any number. So domain is any real number. You can choose whatever real number you like. Then range. Range is set of all possible outcomes. Set of all possible y values. If you go back to the graph, we get only positive y values, not negative y values, not even zero. So range is the interval from 0 to infinity, not including 0. There is no x-intercept because the graph actually it stays above the x-axis all the time. It never touched the x-axis. So there are no x-intercepts. Why? There is only one y-intercept. It happens at 0, 1. And in addition to this, so if you think about 0, 1, It is pretty special. It does not depend on the value for b. Always when x equals 0, regardless of the value for b, it is function gives you 1. If x equals 1, y value is b. If x is minus 1, y value is 1 over b. So, uh, so you see, here in the graph, we always get positive x value, positive y values. And for negative x values, still we get positive y values. And graph, the y values decrease with negative x values. So the graph is closer and closer to x-axis. It seems like it touched the x-axis, but it never touches the x-axis. If you zoom it, you can see it never touches the x-axis. There is a gap between graph and x-axis all the time, and this gap getting smaller and smaller as you increase. If you go further into the negative x-axis, but there is always a gap. But it looks like it touched the x-axis. Because of this reason, we say x-axis is a horizontal asymptote. The meaning is it may happen that at infinity they will touch each other. So whenever you see something comes closer and closer to the horizontal line, we say that line is a horizontal asymptote. Same thing happens with vertical lines. So if there is something like that, we call that a vertical asymptote. But for exponential functions, we don't have vertical asymptotes. Function is 1 to 1. As x increases, f of x increases, but if b bigger than 1, and if b is something in between 0 and 1, function gets decreased. Graph is continuous. There are no breaking points on the graph. So look at the graph of these two functions, 2 to the power x and 3 to the power x. Since 3 is bigger than 2, the graph of 3 to the power x kind of lies above the graph of 2 to the power x in the first quadrant. But for negative x values, the function with the large base decreases fast. So when you go to the second quadrant, this blue color graph is actually goes below the red color graph. So 2 to the power x and 3 to the power x. That's how they looks like when you plot them on the same plane. For positive x values, 2 to the power x is smaller than 3 to the power x. But for negative values, it is the other way. Right? So, but both of them goes through this special point 0, 1. Now imagine you are a very tiny ant on this point. Okay? You see, if you're very small ant on the point 0, 1, you see how these functions goes through the 0, 1. But you cannot like recognize them. Okay, give me a second. Oh, okay. Oh. Maksud ini. Nah, Right? Right. So if you have a very small ant on this point 0, comma 1, you see all these exponential functions goes through you. Okay? Uh, and based on the graphs, you can see which base is bigger, which base is smaller. And if you think about those, um, there should, if it is, if the, if you are really small, you only see a very small range around you, very small region around you. So for you, you won't see the curvature of the graph. You will see on them like like lines. When you keep zooming the curve, uh, the curvature disappears and you see them only as lines. Hmm? That is, the same thing happens with us. If you think around, if you look around, you won't see the curvature of the world. You'll see it as a flat plane. But globally, it is a sphere. For us locally, it looks like a flat plane, unless there are hills and mountains around it. Yeah, so for an ant to distinguish these pairs, what you can use is this line, like line that touches the curve, line that approximates the curve. So among those lines, there is a very special line, line with slope 1. Okay? So the line of, if think about the line with slope 1, then the corresponding base is called the natural base. This is, so people call this the natural base. The way we choose, when we found base, natural base is not straightforward. You won't see why we call it a natural base and why we give it a special name. But I can guarantee you that at the end of our next chapter, you will see why it is so important. So this linear approximation, or this line that touches the ground, it knows about the function, it knows about your exponential function. So this function, so this exponent whose slope at 0, 1 is 1, called the natural base, and when people compute it, it is something in between 0 and 1, something between 0 and 1. For 3 to the power x, slope is slightly bigger than 1. For 2 to the power x, the slope is slightly smaller than 1. A number between 3 and 2 gives you exactly slope 1. And when people compute it, it turned out to be like 2.71828, and you can compute it for a few more digits if you want. This number is called the natural base. Initially, this number may not seem special, but it is significant becomes apparent in the chapter, where you will discover that it simplifies many theoretical computations of derivatives. All right, so here in this slide, you can see different exponential functions in the same plane. So if you look at this right bottom corner, you see both 2 to the power x, e to the power x, and 3 to the power x in the same plane. The green color one above O is 3 to the power x, then one below O is 2 to the power x, In the middle, you have 3 to the power of x. Right. Then, so that's all, pretty much all we need to know about exponential functions at this level. We need to know them as functions. So as functions, we need to know the domain, range, intercepts, if there are any special points, if it is one-to-one or not, and how the graph looks like. Now, the exponential function we saw as a one-to-one function. If it is a one-to-one function, we know it is invertible. So there must be an inverse function for them. And using the graph of exponential function, b to the power x, remember we can deduce the graph of its inverse function. We take the line y equals x and think of y equals x as a mirror, then the mirror image of b to the power x should give us the graph of its inverse function. We know it is invertible, and we know the graph of this inverse function. Let's give it a special name and called logarithmic functions. Logarithm functions are nothing but inverse of exponential functions. So now we are going to study log functions. Again, we need to know the definition, domain, codomain, graphs, and some special properties like we saw properties of exponentials, equations, and if there are any applications. There are a lot of applications of log functions. You have already used them in your O-level classes, A-level classes, especially to simplify computations using log tables. Then other than that, in physics class, they will show up as show up in the Richter scale to measure magnitudes of earthquakes, decibel scale to measure the intensity of the sound, then pH scale to measure the acidity of the solution. Do you have any questions, Malsiluni? She has raised her hand, so do you have any questions? All right, if you have any questions, please put it in the chat, or you can unmute yourself and ask. Then entropy, and there are many applications of log functions. Log function is the inverse of exponential functions. So this is how you define them. So what you do is you take the exponential function, interchange x and y, then you need to solve it for y. Now, so here solving means you need some kind of notation for that. If you have like, when you're solving something, you need a notation, for example. If it is a power, you need to extract the power, you take a root, and so something like that. So here we need a special notation. If p to the power y equals x, then you say y equals log b base x. So always you can change the log expression to an exponential expression. So there is a way to interchange between logs and exponentials. So because of this interchanging rule, you can turn log equations to exponential equations, and solve them using the rules that we know through exponentials. And also, we know some special properties of exponential functions, like the product rule, power rule, quotient rule, and all these nice properties of exponential functions. Because of this equivalence, those properties will reflect as some properties of log functions. So there will be a nice properties of log functions. We already know the graph of exponential functions, and therefore we know the graph of log functions. So in this picture, you can see the graph of 2 to the power x. Their base is 2. Because of that, we know the graph of log 2 base x. The exponential function always passes through this point 0, comma 1. Because of that, when you take the reflection, the x and y coordinate get swapped. So it will pass through, the log function will pass through the point 0, 1, 0, 1, 0. So this special point will be on all the log functions as long as you have a nice, yeah, it is true for all base values actually. And we talked about the horizontal asymptote for the exponential function. When you change the roles of x and y axis, now the y-axis will become a vertical asymptote for the log function. So exponentials have this horizontal asymptote. For the same reason, log functions have this vertical asymptote. Right.
This meeting is being recorded.
Right. Somebody asked my permission to record the video. I gave her the permission, but now there is a box appear in the screen. How can I remove it? Okay, now it is gone. All right. Now let's talk about properties of log functions. So logarithm as functions. We already know the domain and range for exponential functions. For the inverse functions, we switch domain and range. So domain of the log function is the codomain or range for the exponential function. If you look at this graph, domain, that means possible x values for the log function are positive x values. You only see this graph for positive x values. When you go to the negative x value range, you don't have a graph. You don't have a log graph. So domain for the log functions is 0, infinity, open interval. And range, you see, you think about this graph, for any horizontal line, that means for any y value, you have a corresponding point on the graph. So range is minus infinity to plus infinity. We don't have a y-intercept, but there is a single x-intercept. And also, we talked about these special points of the exponential graph. For b to the power x, when x equals 1, b to the power 1 equals 1. So you have 1 comma b on the graph of exponential function. And that one reflect on the logarithm graph as point b comma 1. No horizontal asymptotes, but y-axis is a vertical asymptote. Graph of an so remember, logarithmic function is the inverse of exponential function. So inverse of a one-to-one function. Inverse of a one-to-one function is also one-to-one. So logarithm is another one-to-one function. Then we have this, we talk about the natural base for log functions, E. It has this very peculiar property, but I promised you to discuss about that further in our third chapter. So for now, let's accept the fact that there is a special value that we can choose for the base. So for that b value, we can again talk about corresponding log values, log e base x. This is called the log with natural base. So log natural base e, usually we write it as ln x. To say ln means log with natural base, base. Then in our school, in our O-level classes, we use these log tables. In those tables, they have computed log base 10. This is called the common base. This is not the natural base, but common base is, we use our numerals like that. Hindu Arab numerals, they are in base 10. So likewise, common base for logarithm is 10. And there is a way for changing the base. If you say, if you know the log base c, so you know something base c log, you have tables and you have everything. Let's say you want to change base c from base c to base b. What you do is you take the log c base a and divide it by log c base b. It looks like, so this formula is kind of have this like visually it seems like c cancel with c and b base become b becomes the base. So it is kind of sometimes it is useful to memorize this formula, base change formula. So then the properties of log, properties of exponentials gives you some properties of log functions. The first property is log function is 1:1. If log b base x equals log b base y, then x equals y. Then those inequality rules that we have for exponentials give you some inequality rules for log functions. If b bigger than 1, large x values gives you large log values. That is how we should think about it. Then the product rule. Remember, b to the power x times b to the power y equals b to the power x plus 1. That means when the bases are equal, exponents get added in the multiplication. So that rule reflects as a property of logarithms. Log of a product is sum of logarithms. Log of a product is sum of logarithms. On the other hand, for exponents, it was product of exponents is the sum is like sum of exponents. Sum of these powers. Then the quotient rule, power rule, and since exponentials and logarithms are inverse functions, we have these cancellation rules. B raised, so it is like f of f inverse x equals x. So because b and log are, so the exponents and logs are inverse functions, means they cancel each other. So we have these cancellation rules between those functions and special low values. You can derive all these properties of log functions based on the properties of exponential functions. So right after this class, you should go through this one more time and make sure you understand the meaning of each and every statement within the PowerPoint. So for your, I will put this note into the chat so that you can it should be in the chat, I think. All right, so let me quickly go through some applications of log functions. Some examples with log functions. Simplifying log expression is kind of useful, and for this we use the properties of the log functions. So look at here. We have sum of two log expressions with the same base 2. So log 2 base 1/8 plus log 2 base 64. Now, this is, remember, sum of two logarithms means product of a something inside a single log expression with the same base. So this is same as 2 base 1/8 times 64. So log 2 base 8. Log 2 base 8 is log 2 base. You can write 8 as 2 to the power 3. Then you can, log b base b to the power x is same as x, because you can bring the exponents to front. So these logarithms, what they do is they take these exponents and make them coefficients. We can see it from this power rule. So log b base x to the power n is n log b base x for any number n. And we also have log b base b equals 1. So using those two rules, we can simplify log 2 base 2 to the power 3. That's simply 3. Now, then using this combination of combining all these rules that we learned from logarithms, you can simplify log expressions. They turn products into summations, quotient into differences, powers into multiples. That is what the logarithms do. They simplify things. Then here is a nice application of logarithms. Let's say a biologist estimates that the population of a bacterial colony is given by some constant P naught times 2 to the power kt. If P naught is the initial population. Get this. This is a function. Population is a function of time t. You have this initial population P naught as a constant term. We take that number and multiply it by 2 to the power kt. Here k is some constant depending on the population growth. It may depend on the type of the bacteria. It may depend on the medium that you're growing the bacteria on. So maybe the nutritional level, something like that. K depends on that. And T is time. So 2 to the power, so this T is like 2 to the power T raised to power K. So that means we know the exponential functions grow very fast. So the population must be growing very fast. So far, we don't know the initial population and constant K. Let's read further. Suppose the population is found to be 1,000 after 20 minutes and that it doubles every hour. So somebody has made some observations. After 20th minute of this process, there are 1,000 bacteria in the medium and every hour it doubles. So that means after 1 hour and 20 minutes, there will be 200, so 2,000. After 2 hours and 20 minutes, there will be 4,000, likewise. So that means initially there were T naught amount. When T equals 60, so T we measure in minutes, that means after the 60th minute, there will be twice as the initial population. So when T equals 60, there will be 2 P naught number of bacteria. So now take this equation and solve for K. So it turns out K equals 1 over 60. So that is the constant determined this growth of bacteria growth. And using this K value and the observation that there are 1,000 bacteria after the 20th minute, you can solve for P naught initial population. Using a calculator, you can approximate the P value if you need it to be an integer. But this is good enough. So, when you know the population model, population growth according to this function, and you know some observations, you have some information about the process. It may be the number of bacteria after some time, or it may be the fact that it doubles every hour, or it may be the fact that the population reached to its maximum level after 30 hours or something like that. If you have some information using this model, you can find some useful information. You can deduce how it behaves in the future. Also, you can plot the graph if you want. So this is an application of exponentials, and there are other applications of the same type. So let me skip these applications and move on to our second chapter. Second chapter is called limit and continuity. So we talked about functions in general, and exponential and logarithmic functions are two special types of functions. Limit and continuity is again a general discussion about functions. So imagine graph of a function. Imagine graph of a function. It can have broken points like this. You see, when x equals 1, there is a hole, or when x equals 6, there is a vertical asymptote, or when x equals 4, there is a gap. So this kind of behavior appears in the graphs. So you might ask for an example. The best I can give you is think about the word piecewise linear. So when there can be gaps, I'll show you some examples. So limit and continuity is about the behaviors of functions when there is a gap or a breaking point of the graph. Limit of a function. Limit of a function is discuss about behavior of a function at a breaking point, especially. So let's forget about breaking points for a second, and let's call limit of a function is the behavior of the function as x gets closer and closer to a particular number. So let's say this particular number is 5, then we say the limit of f as x reach to 5. So think about this function. F of x equals x squared minus 1 over x minus 1. X squared minus 1 divided by x minus 1. In the denominator, you have x minus 1. Therefore, function is undefined at 1. So our domain includes all the real numbers except 1. So the function looks really nice except at 1. So how can we deal with this bad point? 1. It is just 1 there. No, all the other points are really nice except 1. So to deal with that, you can simplify this expression. Sometimes you can simplify this expression. It is not always possible, but sometimes it is possible. If you think about x squared minus 1, it has a factorization, x minus 1 times x plus 1. So since x minus 1 appears in both numerator and denominator, you can cancel them. So the expression simplifies to x plus 1. So initially the function was really bad, but now we have simplified it to a very nice one. Y equal x plus 1 is a line. You can see the graph of that function. Graph of y equals x plus 1 in the left hand side. This function is really nice, but initially we said x not equal 1, so we have to go with that. So this is nice, really nice, except at 1. Because at the very beginning we said x not equal 1. So we have to live with that. So graph of this function f is a line with a pole at x equal 1. When x equal, so if you forget that restriction, when x equal 1, y should have been 2. So if this was not a bad point, y value is 2. But now it is not the case. We cannot set x equal 1. It is not allowed. Now, what we can do is, we cannot set x equal 1, but you can get closer and closer to 1 and observe what happens to y values. When you pick a very large, some value bigger than 1, and get closer and closer to 1. When you get closer and closer to 1, for that x value, you have a corresponding value on the line, and this y line has two pieces, this upper part and the lower part. For x value is bigger than 1, we need to consider this upper part, and as we reach to x, we are sort of going down towards this point 1, 0. And also for x values below 1, we are climbing up on the line and reach to point 1, 2. So x not equal 1, but still we can talk about what happens as x get closer and closer to 1. In that case, from either side we are approaching to the point 1, 2. So this is what we call the limit. When x goes to 1, limit of the function is 2. 1 is not in the domain of the function, but as we reach to 1, limit of the function is 2. Right? So this is what we are dealing with in this chapter. So now we need a notation to show the fact that we are not setting x equal 1, but we are taking the limit as x goes to 1. So we write this as limit x goes to 1, function value equals 2. Right? So limit as x goes to 1, function value equals 2. This is not like f of 1 equals 2. This is different. So limit as x goes to c, f of x equals L. This is the general notation. So we read this as the limit of f of x as x approaches to c is L. So in general, you can talk about one-sided limits. Remember, we talked about the ways of approaching 1. You could approach to 1 from the left-hand side, or you could approach to 1 from the right-hand side. So here, if you approach to 1 from the right-hand side, you are this sort of climbing down. And reach to 2. And if not, you can climb up and reach to 2. If you go to 1 from the left-hand side, that's what happens. So we can talk about one-sided limits. The direction that you are approaching to C. If you are approaching to C from the right-hand side, we write it as limit as x goes to C from the right-hand side. This plus sign denotes the direction. Plus is for the right hand side and minus is for the left hand side. So one-sided limits. In the last example, the direction does not matter. It was the problem when we go to one from the left hand side and one from the right hand side. We always got two. So the both left limit and right limit equals to 2. That was nice, but in general, it may not be the case. Let me show you. Yeah, look at this. In this picture, when you approach to 4 from the left hand side, when you approach to 4 from the left hand side, function. So you're going down. This is like slide. So when you're sliding down on the graph, you reach to y values reach to 1. So as x goes to 4, left limit is 1. Now take some value bigger than 4 and look at the corresponding part of the graph. Now as you approach to 4, right limit. From the right hand side, y values are approaching to 4. So left limit and right limit can be different. If those two are different, there will be a gap. There will be a gap here. Left limit is 1, right limit is 4. So there is a gap of 3 units. But in the example, both left limit and right limit are equal. So there is no gap, but just a hole. If there is a hole, both left limit and right limit are equal. If there is a gap, that means left limit and right limit are different. So sometimes these one-sided limits helps us to see the difference, whether there is a gap or a hole. One-sided limit theorem. It says the two-sided limit exists if and only if the one-sided limits both exist and equal. That means that if the right limit and left limit are equal, that means we don't need to worry about the direction or how we approach to point X. In that case, you can write it without specifying the direction. Without specifying the direction. Here's another example. In this graph, you can see part of a parabola and part of a line. So there is a problem at x equals 2. When you approach to 2 from the left hand side, that means you need to consider the parabola. So parabola goes up and up and up, and at 2 it's reached to 4. So left limit of the function as x goes to 2 is 4. For the right limit, take something bigger than 2. When you take something bigger than 2, you need to focus on the line. But on the line, you're sliding down, and as you approach to 2, function values approaches to 3. So the right limit as x goes to 2 is 3. So now we have both left limit and right limit, and they are different. They are different because of their difference. There is a gap between these two pieces. So the one-sided limits exist, but they are different. Therefore, the two-sided limit, the common value does not exist. If there was a common value, we don't see a gap. We will see probably a hole. Again, you can see from this graph, there is a curvy part in the right hand side, and there's a horizontal line part to the left of the picture, and there is a gap occurring at -4. So you can compute the left limit and right limit separately, but because of their difference, the two-sided limit won't exist. So there is no two-sided limit or common limit at x equal -4, but one-sided limits exist, and you can find their values using the graph. Okay, somebody needs this, so I will put it in the chat. Don't worry, I will upload the LMS after the class. All right. So in the second example also, the two-sided limit does not exist at -4. Look at this. This is kind of important. I hope you remember the graph of 1 over x. Graph of 1 over x, it is a parabola. For positive x values, y values are positive. For negative x values, y values are negative. The function is well defined except at 0. Because at 0, you're having something like 1 over 0, which is meaningless. So the function this function has this bad point at 0. So what happens near the 0 is, for very small value, let's say for a very small positive value, y value becomes very large. For example, let's say x equals 10 to the power -10. After taking the reciprocal, it becomes 10 to the power 10, which is huge. 10 to the power -10 is a very small number. You cannot even measure it using a ruler. It is a very small value. I'm not sure whether you can even measure it using a microscope. It's very small. But after taking the reciprocal, it becomes huge, 10 to the power 10. The same thing happens with negative numbers. For a very small negative, like negative number with a very small absolute value, you get a very huge negative number. So we say when you go to 0, let's say from the right hand side, on the graph, you're climbing up and up and up, and you're going to infinity. So we say, as we go to 0 from the right hand side, we go to infinity. So infinity is not a number, but it is a symbol. It is a way of denoting that you're increasing without no upper bound. There is no barrier. You keep going up and up and up forever. And same thing is true as you go to 0 from the left hand side. Now, what you're doing is you're sliding down, going down forever. There is no stop. So you are going to reach to minus infinity. So both left limit and right limit are infinity. One is positive infinity, one is negative infinity. We call them infinite limits, but they are different. Because of they are not equal, the two-sided limit does not exist. Here is a very strange behavior. You don't need to worry about this that much, but I'll show you. I'll discuss this to show you there can be some very strange behaviors. For example, think about the graph of sine of 1 over x. The graph of a sine function is a wave like graph. It goes up and down. There's this nice looking wave type shape. So that's how the graph of sine x looks like. But remember, 1 over x, it is a nice function. You can compute it everywhere except at 0. So as you reach to 0, you should expect some strange behavior. We had something with infinite limits for the graph of 1 over x. But for sine x, remember, sine x is always some number between 0 and 1. So sine x, there will be no angle like sine theta equals 2. Sine values are always some numbers between 0 and 1. So this is a graph of sine. Once you combine sine and 1 over x, you can expect a very strange behavior near 0. So what happens is, as we go to 0, the function keep going up and down very rapidly. It goes up and down very rapidly, and I cannot zoom it without making it blur. So what happens is it goes up and down very rapidly, and there are like infinite. It goes up and down infinitely many times. So near 0, it has this very fast-moving nature. Because of that, you cannot say what happens near 0. So we say the function does not exist. The limit does not exist as a result of this very rapid oscillations. Yeah, so this is a very strange behavior, and we don't need to worry about these type of examples. They are very rare, but I included it as the last slide of this part to show you there are strange behaviors. This is a very unique, strange behavior because you're composing two very special functions, one over x and sine x. When you compose, their properties very different, but once you combine, you get an even stranger behavior. Right, so that's about limits. So in this section, we learn what a limit is, like an intuitive divisor. We saw there are two types of limits, left limit and right limit. If those two are different, there is a gap in the graph. If they are equal, probably there will be a hole in the graph, and we say the common value is the two-sided limit. So sometimes this two-sided limit exists and sometimes it does not. And sometimes we can get infinity or minus infinity as the limit. Yeah, so that is roughly intuitively what we mean by the limit of a function. So let's talk about computations. So we saw one example, x squared minus 1 divided by x minus 1. For that example, we computed the limit. But in general, how can you compute the limit? What is the process of computing it? there are a few laws, limit laws that we can write down and use to compute things. The first rule says, let's say our function is a constant k. If it is a constant, limit does not have a meaning. So let me share the writing pad. So think about the constant function f of x equals 2. In the graph of this function, y equal f of x is y equals 2. Y equals 2 is a horizontal line. Now take any x you like. Function value is always 1. As you go to x from the right hand side, on the graph you're reaching to this point. Now let's say you go to x from the left hand side. Now you're approaching to the same point from the left hand side. The common value, the two-sided limit exists and it is 2. So the left and right limit, for a constant function, left and right limit won't be a problem. The limit always exists and the common limit is the constant. So if you think about y equals k, as x goes to any c value. Okay. Let me name it as c. Now, as x goes to c, limit of the constant function k is k. It doesn't depend on the c value. It is always k. Oh. So then, right. So, yeah, limit of a constant function is the constant. So that is what we have said in this verse. Let's look at the function. F of x equals x. We also know about this function. The graph is a line. that goes through the origin with slope 1. Now let's pick some C value. And as we move to C from the left-hand side, on the graph we are reaching to this point, and y equals x. So at this point, y equals C. The same thing is true when we reach to C from the right-hand side. We are moving down and we get the same value. So both left and right limits exist, and therefore the common limit exists. As x goes to C, the function x equals C. Y value is C. That means if you set x equals C, x equals C. So limit as x goes to C, x equals C. When x goes to 2, so you can see some numerical examples in the right hand side. When x goes to 2, x equals 2. Then second two, last two properties. Let's say you have some constant times x and you know the limit of f. Then you can forget about this constant in front and put it aside and compute the limit. So for example, when x goes to 2, 3x. Keep 3 aside. We know when x goes to 2, x equals 2. Then 2 times 3 is 6. That is how we get 3. Think about the limit of this number and multiply it by 3. So you can multiply limits by constants like this. The last property is, say you want to compute limit of a summation. You can compute limits of these individual parts. These are parts separately and at the limit. So for example, if you the limit of 3x plus 5 as x goes to 2, limit of 3x is 6 and limit of 5 is 5 because 5 is a constant. So 6 plus 5 is 11. So we can use these limit laws to compute limits. The constant rule, then identity rule, scalar multiples, summations, and even we can go through products and quotients and powers. Product is nice again. If you want to compute the product of a limit, limit of a product, you compute limit of individual factors and then multiply. Limit of 3x plus 5 times x plus 1. As x goes to 2, 3x plus 5. It substitute x equals 2, then this should be 11 times 3, 33. Then limit of a quotient. This is this is a point where you need to be careful. So when you compute limit of a quotient, you need to make sure that the denominator is non-zero. Sometimes it can be 0. If it is 0, this rule does not hold. It is not going to work. If the limit, if the taking limit gives you something non-zero in the denominator, limit of the quotient is quotient of limits. You can take limit of these factors separately. Then when you take a limit of a power, let's say power n is fixed. It is some fixed number. It has no x terms in it. In that case, like the product rule, you can, like the constant multiple rule, you can take the power aside and take the limit, and then find a place to the power. So this is square root. Square root is power 1/2. No externals in the 1/2. So you can put 1/2 aside and take the limit of whatever inside the square root. So yeah, so using these rules, we can compute limits. Let me give you some examples. So x goes to 1, limit of x plus 1, x minus 2 divided by x squared plus 4. That is the limit of this expression. So the idea is, so whenever you have to solve a problem, limit problem like this, take a separate paper and substitute 1 into this expression and see what happens. So do this in a separate paper. Okay. So substitute 1 minus 2. One square plus 4. So this is like a secret computation. We don't show it to anyone. So we get 2 times minus 1 divided by 5. So this is minus 2 divided by 5. So we did not run into any problem in the substitution process. We did not encounter any problem. We got a genuine number. If there is something like that, that number is the answer you are looking for. So the answer for this limit problem is 2 divided by 4. So nothing fancy. So if there is no problem, directly substitution. If the substitution produces a nice real number, then that's what we do. The limits are useful when there is a problem. When you have a genuine problem, you need limits. So let me give you another example. Right? And again, let's take a pen. Let's take a separate piece of paper and do our secret computation. So let's say when you set x equals 2, you get 4 minus 10 plus 6. So now we get 0 because we get 4 minus 4. What is it? In the numerator we get 0, and in the denominator we get another 0. 0 divided by 0. A really bad situation because we are not allowed to divide by 0. Not only that, we are having a 0 in the numerator as well. If we had something like 2 divided by 0, we say this is undefined. This cannot happen in a number system. But when you have something like 0 divided by 0, what happens is sometimes you can simplify this expression before evaluating it. Maybe you can simplify it and find something, assign a number. So this assigning a real number for these type of expression is what we call limit. So here, this direct substitution does not work. If it worked, the direct substitution is a genuine way of evaluating limit. But here, we are not having a genuine real number. We are having something meaningless, 0 divided by 0. It is not even undefined. 0 divided by 0 is not an undefined thing. We cannot ignore it. We should simplify it and find something. So in this case, what we can do is we can factor this. So look at this. Let's see whether we can factor this. Yes, we can. So x minus 2, x minus 3. And then not only numerator, denominator also has factors. If substituting 2 gives you a 0, that means x minus 2 is a factor. The other factor is easy to find. Now, there are common factors and simplify those. Cancel out. If those are factors appears in the both numerator and denominator, that means they cancel out. After cancelling them, again take your secret pen and the paper and compute. Now substitute 2. 2 minus 3, 2 plus 2. So what you get is minus 1 divided by 4. Yes, after simplifying the expression, one time we get something. We get something after direct computations. You see, this is not 0 divided by 0. That is gone because we have cancelled out the common factor. This time we get a nice real number. That is the limit we were looking for. So as x goes to 2, the limit of that expression is not 0 divided by 0. It is not undefined. It is negative 1/4. So you see, we found something genuine, some genuine number. So both left limit and right limit must be equal. There won't be a gap in the graph, but there will be a hole in the graph. Right? Yes. So let me give you an exercise, and you should work on that. To compute x goes to 2, x minus 2, x squared minus 5x. Let me make it something like so this is for you to simplify. I'll stop the class at right here. It is 11 o'clock, so you might be tired by now. I will update the LMS page later today. Yeah, I think, yeah, I up I update the LMS page. I remember I had updated the LMS page after the last class, but something happened. Probably I uploaded but did not save, I think. Yeah, I think I did not hit the save button. So I'll do so. Uh, all right. Uh, do you have any questions or anything to ask before I stop the Zoom session? Okay. Uh, Somebody asked, when do we have the midday exam? That's a really good question. We should have it soon. Maybe after next chapter. Because so far, until the today, what we did was we were recalling the previous back things that you know. You knew about equations, inequalities, integrals, functions. Probably you have not studied them in the mathematical perspective, but you knew those. You knew the graphs. You knew these geometric transformations of graph. But now we are studying them in a more mathematical way. So even exponentials and log functions, you know everything about them, but maybe not in the way like mathematics students know about it. Uh, Today we started something branching out from your previous knowledge. You have not seen limits before, I suppose, and so we started this new topic. This is the beginning point of calculus. This is the beginning point of mathematical analysis. So you need to know about limits very well. You have one week until next Monday. So during this time, please read my notes and not, but do not depend on my notes and my discussions. You can go to internet nowadays very easily and find a lot of YouTube videos, a lot of lecture notes, a lot of interactive kind of things. So watch those videos, learn as much as you can about limits. You don't need to go very deep. Simple computations of limits will be helpful, right? Right. Yeah, I will update all the notes for chapter 2 and 3 in to the limits. Right. Thank you for that suggestion. All right. Have a nice day and enjoy the rest of this week. Good luck.